Good afternoon.
Good afternoon.
As you know, a week from now will be the test. Please, if you didn't start to prepare, please do it soon, because this big set of questions will be not easy to answer without studying. And I uploaded the most recent presentation to the Moodle this morning, this very last one. Plus, I uploaded a little modified questions too. When you will take a look in it, you will see big part of it marked blue, meaning that the blue will be not in a test. Still, there are a lot black remained in the list, and the way to do that, you need to go through step by step. And I encourage you, if you don't know anything about that question, please answer it. And if you know something about it, you can go to the next one, but you don't know anything about it. And I hope I am not totally misinformed, but I think if you will get any of these questions from the list, that could be a good discussion topic with your friend or with your girlfriend or who you respect, because those areas are extremely interesting and current things, and I really hope it is good to know the answer for those questions. Today I am going to cover two topics. Each of them can be extremely big. Since I have only 2 times 45 minutes, I need to shrink something within this small time frame. The first one is the sensors. As we agreed, as I told you many times before, if you want to make a smart behavior, the whole thing starts with the sensation, the sensing. Because if you cannot sense what the situation is, what the problem is, how can we solve it smartly? So the very first element is the sensor, and we are in an age of the sensor age, because unbelievable progress was made in the last couple of years in the field of sensors. For example, visual sensors, cameras, or auditory sound sensors, microphones, and many different fantastic, interesting things. I wish to be able to talk about details for all of them because they are fascinating, but I don't have time. What I have time, I choose this method intentionally. Rather, I will talk about the biological sensors. Not because we can use it right away, it is built in our body, so we are using that right away, but we cannot mimic it in a right away. We need to do effort somehow make something as good as the biological sensor. But if we will understand the main concept behind those, we see at least what is the good, what is the target, and we can make something as good, or we can make something even better what was there. So this is the list of the most important elements of the intelligence, what I told you several times. The starting point is the sensors. I also told you several times before, the human brain, what is kind of model for our computing models these days, it is not a universal machine, not a non-von Neumann machine, not a Turing machine. It is a specialized biological parallel processor. This picture, what it shows for you, it was very fascinating for me, at least this part, what you can see here. They use the state-of-the-art so-called MRI technology to monitor the activity in a brain. It is not an X-ray to show what is solid in it, rather it measures what is active in it. And for example, when this person was in this MRI machine, probably he was asked, read something, and there was a paper in front of him. The first thing was just look at it. And when he looked at it, this area was active. And then the next question was for him to read it loud. So when he read it loud, this area was active. And when the question was, please think about what is the meaning of what you read, this area was active. So meaning that different parts of the brain processing those different informations. And it was well known before, even before the MRI, because the guy, whose name was Brodmann, and many of his colleagues, discovered that if they will cut slices from the human brain and paint it with a different kind of dyes and put it under microscope, they would find different structures. And that time it was not well known what is this structure is good for and why it is connected like that. These days, we already know the specific structures. For example, this area, it is very good for visual information processing. We are mimicking that. These convolution networks, what is very common these days, try to mimic this area. And we also know a lot of things about the different areas. What is the different area is responsible for? And I can vision very easily that in the close future, we will have a specialized brain-like computers mimicking one specific area of the human brain, doing something even better what we can do within our lifetime. Not in a far distant future, it will be in our lifetime. So it is fascinating. And maybe it is an engineering approach what I'll try to at least do here at the first some steps. We need to look at what is inside. We need to understand the core elements and then how the core element works. And we can learn a lot of things from it. This is my goal for the first part of this lecture, to show you these lessons, what we can learn from the biological information processing device, the brain. This is a cross-section of the human brain. You can see these are the processors here on a cortex here. These are the processors, these areas. And the other are the cables, what is connect them. Using different kind of paint or dyes, we can visualize those different cells. What is a connection cell, for example, here, or the processing cells on a surface. And if you want to see what is the distribution of this processor in our brain, it was discovered a long time ago, and it is kind of interesting to learn. For example, if we will measure the activity on a brain using some electrodes, we can tell which area is active. Not just the MRI technology, electric technology is also good for that, to measure which brain area is active processing some kind of information. What we learned, for example, the somatosensory, to sense our body, it is somehow distributed on a brain, something like that, in making a section here in this area. Meaning that, for example, this whole area here processing the face. This area here processing the leg, the upper leg. This area here processing the foot. And this big area is processing the thumb. To looking at this photo, it makes sense why we are using the thumb to handle in the smartphone. Because the thumb is extremely smart. Huge processor belongs to that, a lot of sensors built in it, extremely fascinating how it can move because of this big processor area here. Our little pinky is not good for that. It is not good for anything because we cannot move it. The processor is extremely small somewhere here. It is almost negligible. But the thumb is not. It is very important. Also very important area, the face. This is a reason why we are watching faces all the time. This is how we communicate. I'm not looking at your shoulder. It can be interesting, but I'm looking at your face, because the face can show me many things, and because the huge processor behind that. And this is a big processor for the tongue. The tongue is very important. This is a reason why when a little kid is in his infantry stage, let's say half-year-old or something like that, when his visual system is not so very sophisticated, what we have in all the time, then the person is put everything in his mouth, not because he or she is hungry, because he wants to test it. This is the way to test it, because this process is already there, the tongue is already there, a lot of sensors on it, and easy to touch something with it, easy to discover what is that, edges or tastes or something like that, because there are many, many sensors built into the tongue, for example. And we know already this area responsible for the movement, this area responsible for the sensation. And the distribution is something very similar for the movement and for the sensation. One of the interesting discoveries was we don't have 100 different types of neurons. We have just some dozen different kinds of neurons. And each of them has the same common feature, meaning that there is a cell body somewhere in the middle, something like this, like a cell body. And there are many inputs, it is called dendrite, what can bring information into the cell. And one output, only this one. This is called axon. This axon can travel, the information can travel on an axon. As we learned from the artificial neural networks, what was based on this behavior of the biological neuron, this cell somehow summarizes the inputs, what goes on it, on these dendrites. And when this sum of this information, what comes in, reaches the level, some kind of threshold, the nerve will so-called fire. It will give a pulse. And this is the next thing what I like to show you in our next photo. here. Not this one, just a little later. Before we go there, I'd like to tell you, it is a very fascinating to recognize. These days is a very, very dominant trend in AI that so far till these days, the digital computer was the most dominant. But focusing on the AI areas, more and more development can be found in the analog field, somehow mimicking the analog computers, mimicking the brain itself. Unbelievable. I put together, or actually I collected some readings for you. I think it's fascinating to read, so your free time, to listen what are those hardwares, what was under development these days. Analog computers. These computers can somehow supplement the digital one, what is built in our devices these days. So the way how it works, it summarizes the input. It can be excitatory or inhibitory. As a result, the cell will somehow accumulate the inputs, and when this accumulated input reaches the level, it will fire, it will give a pulse. This is the common feature for each of the neurons in our nerve system. Unbelievable, but it is true. And what is also like to point out very briefly here, that the way how the information travels in a nervous system, it is kind of pulse modulated. Very interesting to understand, because it is fault tolerant. If we would just send signals, let's say one level, this level can be changed easily because any noise can influence it. Some induction from the electric system or something like that. But since it is not a simple electric signal, rather a pulse modulated signal, it is fault tolerant. So we don't move our finger just accidentally because of some electric current around us, because we need to send dozens or maybe hundreds of pulses to move our little finger. It is something fascinating. And just go back for a second, again here. The processing here is some kind of chemical. We don't know, humans don't know all of the details. We know a lot of how this kind of neurotransmitters works, what kind of chemical should be in this area to transmit the signal. The signal travels electrically through the cable, through the axon. So when they reach this endpoint, it releases chemicals. It is called neurotransmitters. And the neurotransmitters need to somehow match the recipients here, the sensors at the other cell. This is an electrochemical procedure, extremely complicated and beautiful. What I would name it is an analog procedure. It is not a digital. Sending the signal is digital, but processing that it is analog. And this is what we are mimicking these days, and at least half dozen of companies are making analog chips these days. So there are major elements that we need to understand. We're talking about biological sensors. The first one is the modality, meaning that each sensor is good for something. There are no sensor what is good for everything. We have an eye sense the visual information. We have ears to sense the sound between a certain range, between 20 Hertz till 16 or 20,000 Hertz, and so on. So we have a very specific sensor for different kind of signals around us. Each sensor has an absolute stimulus threshold, meaning that there is a minimum what it can sense. Unbelievable, it can be extremely low. Our sensors are extremely sensitive. And then we have a relative stimulus threshold, meaning that what was the original signal level. If the signal level is high, the threshold what we can sense, the difference what we can sense, it is also high. But if the signal level is very low, for example, we are sitting in a quiet room, we can almost hear the atoms bouncing to each other. But we need to wait for a long time to be in that stage to somehow build up our sensitivity in our ear, for example. Or in our eyes, we can almost see one photon coming into our eyes, if our eyes are adapted for the specific situation. This is called adaptation. So we can adapt the level of the information around us. And it's also good to know that there is a so-called refractor stage in each neurons, meaning that if we give some strong stimulus for the nerve, there is some period that cannot react. They need to relax. They need to stay quiet or need need to switch off for a certain period of time. It is also important to know there are many consequences of that. And as I mentioned, the transmission of the signals are frequency modulated, and then the processing is out amplitude modulated analog. It is interesting. This is how the nerve works. Each nerve works. It would be in a test, very likely, so better to understand that. So when we have a cell, something like that, there is a cell body. These are the dendrites what connects to that cell. This is the axon. This is what brings the information. If we would put a needle inside of the cell, because it has a cell surface, and inside there is a body inside, some kind of fluid. If we put a needle in it, and another needle will be outside of the skin or the body of the nerve cell, we can measure voltage between that. If the cell is alive, it is working, we can measure a voltage between this point and the neighboring point. And this voltage usually about 60-70 millivolts. This shows the cell is alive, it is working. So when we are going to give any input for the cell, the result will be somehow this potential will decrease gradually, if we are giving this input gradually, step by step. And there is a certain point, meaning the threshold. When we reach this point here, the cell will say, okay, enough, I will do something. It is called action. It is called the action potential, what we can measure that, meaning that the polarity of this potential inverses. The why it is the original potential is there because the cell has a very specific effect in it, specific ability to separate sodium and potassium. Potassium and sodium are differently concentrated in the boundary of the surface of the cell. It is an active procedure. And when we will reach the threshold, somehow these gates are opening, and then this whole potential will reverse. This is what we can measure here, jumping from minus 40 millivolts up to positive 40 millivolts. Let me show you this. This is the point, what we are measuring, this point. When the cell is in a relaxed stage, we have a minus 7 millivolt inside, and when we are reached this threshold, it will jump up, and if the cell is alive, eventually it will bring back those potassium and sodium, and it will go back to the basic level. And there is some ripple at the end. This is the so-called post-potential. And each of the cell acts like that. If it will reach the threshold, it will produce a pulse. And eventually the pulse will go back for the baseline. The question is here, what happens if the signal is bigger? What do you think? It cannot give a bigger signal, it will give the same size of signal. The size of the stimulus, what will go into the cell, will modify that how often we are going to sense this input or this signal. It will come faster or more frequent when the stimulus is stronger. If it is weaker, just very rarely. For example, if we want to move our finger like this very slowly, like this here very slowly, we are sending pulses, something like that. But when we are reaching, for example, holding that and pressing that hard, we want to put, then something like that, this fast. One of the interesting experiments what you can test if you like. I was fascinated when I studied this long time ago. When you go to bed in the evening or any time when you're ready to sleep, you put your head on a pillow, something like that. But not pushing the pillow very strong, just a little bit, just a tiny bit, just touching the pillow with your face, and start to somehow squeeze together your jaws. If you were lucky and if you are in the right position, you can hear these pulses. Because the pulse, what somehow push together your jaws, it comes like something like that. And it is fascinating. So when I studied this, there was an option for me to go be a subject for experiments, and I volunteered that. So they put needles in my muscles. It was a kind of bad feeling, but I said, okay, I need to make the sacrifice. I did that. They put needles in my muscles, and it was a shock for me to be able to learn to send only one pulse for the muscle. I was thinking about that. One pulse went to my muscle. And the guy who conducted this experiment said, okay, make it stronger. And I said, something like that. It came many pulses to my, and to make a contraction or build a force, we need a lot of pulses. The same thing applies for the sensory input too. If the sensory input is larger, bigger, we have more pulses. If it is just weak, just sometime, time to time, and the size is the same, almost the same, something like this. This is how it goes. This is the set of action potentials what can travel on the axis, on the axon. This is important to know. There are three major laws somehow what governs the sensations. It's good to know. The first one is so-called the Weber law. This guy, Henrik Weber, invented a long time ago. And the idea is the following. If this is the signal level, this E, this is the signal intensity. And this is the difference what we can sense, what we can notice. If the signal level is very high, this threshold is also very high, very big. If the signal level is very low, the threshold is also very small. So it is something good to know. You can ask, can we use it somewhere? Answer is that yes. For example, the MP4 compression utilizes this interesting law. Because if you listen a very strong sound, what comes into in our ear with the headphones or something like that, in the following milliseconds, there is no need to decode or sample the sound very often. So we can modify the sampling rate after the very strong signal, because we are not able to sense it anyway. So this constant here depends what kind of modality we have. It is different for vision, different for hearing, something like that. It was one of the very first discovery how we sense the world around us. The second law was the so-called Weber-Fechner law. It means that if this is the signal intensity, and this is the perceived intensity, what we can feel, the perceived sensitivity or perceived signal logarithmic to the original input signal. Interesting to know. You can ask why. The simple answer for that, because this helps us to sense a big range. Because it's something 1,000 times bigger than it was before. Using this logarithm, it is only 3 times bigger as a sensation. Because of that, our vision or our hearing logarithmic. We can sense 1,000 times big sound, even if it's not hurt our ears very much, and it is not 1,000 times more loud. Just maybe 4 times, 3, 5 times, something like that. Little later on, there was another person, his name was Stevens, who discovered this logarithmic feature is just partially true. This is how it always happens. He learned there are some certain signals, for example, sound and light, what is logarithmic, something like that. But there are certain inputs what is exponential. For example, like this here, electric shock, temperature, sweetness. It is exponential, meaning that a little bigger signal gives us a huge feeling, huge impression. One interesting, probably already experienced that, it is not a pleasant thing. If you eat a chocolate and accidentally put this little piece of paper, this aluminum foil, into your mouth, and if you are not so fortunate to have a fillings in your teeth, and it was an amalgam filling, way back it was the standard, you can build a battery in your mouth because of this aluminum foil and the amalgamous filling in a ear, in a tooth. It can generate a small battery. It can be extremely painful, and maybe you have this experience. So, good to know that Stephen Law says the perceived intensity, what we can feel, depends on this kind of equation, like this here, when the n is different. N is positive for sound and light, and smaller than 1. That makes this logarithmic. And if it is bigger than 1, it makes it exponential. So this is what we have these days. Because of that, we can sense something electric shock extremely well, and a brightness just logarithmically. This is what we have. The next thing what I like to mention very briefly, we have many sensors in our body. One of the first important thing, our surface, the skin. This is the larger sensing organ in our body. It is full of different kinds of sensors: touch, temperature, vibration, and so on. One of the interesting things what I just like to mention here, the skin has some kind of hair cells in it, something like that. All of the most of the creatures has some kind of cell, some kind of hair on a surface. It serves two purposes. Two goals. One is to somehow as a heat protection. It can make a shade if there is a bright sunlight if it is too many hairs in it, or it can keep a warm if it is the air sits in it and this air can make an insulation, or it can be a sensor, something like this. And if we will modify just a little bit, this kind of level can help to sense it. There are some nerve cells around it at the bottom. So if we will move it just a little bit, even just some degree, we can sense it. And it is good because if we have the cells in our surface, we can avoid the collision. We can go this far and I can already sense it because I'm almost there. That's why the cat has a big whiskers on a face. And if the whiskers will fit somewhere, the cat can go in it. If not, not. Something like that, sensing with this hair cells. And what is important to know, the distribution is totally different. It is not even, not identical everywhere. For example, you can expect where it is very good distribution on our lips and our fingers. You can see it here. On our fingers, the so-called 2-point threshold, it is called 2-point threshold. It is very small at the fingers, very small at the lips. It was a fun lab experiment when I was in school to test this. We had a pair of scissors or a pair of compasses, and we had to touch with the two needles at the same time on the surface of each other in a lab. And it was funny to tell, if you touch it like this here, we was not able to tell it is 2-point or 1 because of the very rare sensors in our body. But here on the lips or on the fingers, he was able to tell between a millimeter distance because so many sensors there. And this graph shows this distribution. The vision is the most important for most of us who have a luxury to have eyes and have a good processor for it. The visual system is extremely complicated and we can learn a lot of things from it. For example, the human vision looking backwards. The sensors are backwards, not forward, backwards. All of the sensors are looking backwards. So what we sense, it is a reflected light from our inner surface, our eye. Why it is so important? Maybe because it's a protection. Protected from the extremely bright light, what comes in our eyes. The second, what is very important to know, the eye is kind of brain structure. When the person is in a development stage, when she or he is in several weeks old, one of the first organs will be developed, the eye. It is part of the brain. And the brain somehow travels out close to the surface of the face of the human. And this is the reason when somebody, the eye doctor will look into your eye, he or she can literally see your brain because there is optical elements in it. Through this optical element, the structure of the retina, it is visible. And you can see all of the veins, you can see all of the arteries in it, and that's why it is extremely sensitive. It is much more sensitive than looking at all of our body parts. Because if somebody will look into your eye, can easily tell your brain status, how old you are, and how good is your brain, how good status the brain has, because the vessels are visible, the arteries are visible. That's why it is very sensitive. This is one of the reasons, as you know, one of the very standard personal identification method, the retina scan, to look into the device and it will scan your retina and tell you who you are, because each of us has a very specific structure in it. Just as good as the fingerprint, but much more sensitive, because if somebody has access to your retina, can tell a lot of information about you. And So good thing it is not easy to access. For example, from this distance, not easy to look into your retina. Good thing we have an iris in it, what focused a little bit, and not easy to look in it. But if somebody asks you to look into the hole and there is a camera, it's a risky thing because they're checking your retina. And they can tell you something, tell many things about you. I put together a list of different kind of features. I don't ask you to learn it. I just inform you. If you're interested, you can look in it, and you can see the huge range what the eye is responsible or sensitive. Extremely big range because of this logarithmic way to sense. And what is important to know here, that we have two different kinds of sensors in our brain, the so-called rods and the cones. And the distribution of these two systems is totally different. The next photo what I like to show you is the following. If this is the most sensitive area in our eye, in a retina, this is called the fovea. This is where all of the cones are. The cones are responsible for color vision or sensing the structure. The other elements, the rods, are responsible for movement and a dark vision. And when we are at the retina, or at the fovea, most of the cones are there. This is the distribution of this red one. And this is the distribution for the rods. Please look at it at home. Maybe it will be in a test, maybe not, but could be. I will ask which one is the rods, which one is the cones. One interesting consequence of this, one interesting consequence of this distribution difference. I'm sure you heard about the situation when a cat is playing with a mouse, and usually not watching like that, because the cat can sense the movement much better on a surface, on a peripherals. So if you want to sense a movement, don't watch it. Just look at it like that. Watch somewhere there, but let the information go to your peripheral part of your eyes, because you can sense it much better, because much more sensors there what can sense the movement. If you want to understand something, if you want to read the very details of the visual information, you need to focus on it. I'm sure you heard about the so-called Retina Display. One of the very common and popular things today. The point is here, you need to have a resolution, the screen resolution, what is better than the retina resolution. If you have something close, you can name the device the Retina Display, and it's very pleasing because you cannot see the pixels. It was a new trend some years ago, and as you see, there are different versions of this. And the main point is not to be able to tell the difference between 2 points. The cones and rods are distributed differently. So we have a night vision sensitivity and a dark vision sensitivity. This is how it looks. This is the total, this is the sum, but this is for the dark vision, this is for the night vision. And technically, it is very important to know we have two different kinds of color generation methods, so-called additive and a subtractive. Both of them is very common these days. And we got used to, we have color screens all around us, and because of the detailed understanding of the visual system. Very briefly, just as briefly as the visual system, I'd like to summarize how we can sense hearing. One of the things what is in a list, please figure it out. What is the percentage of the information what we sense from the environment? What is the most important, the vision or the hearing or the touch, something like that? Please look it up. It can be in a test. So, hearing is also very important. Very important to know we have a complex organ built in our head, like this. This is responsible for hearing the sound, and the other one is responsible for balance, to sensing the balance. And I wanted to show you some small demonstration here. That's why I brought here a skull, real human skull. This is the human skull. And the good thing in it, when I studied the brain structure, I was fortunate to be able to buy this for someone. Actually, I didn't pay for money. I just got it and this skull was in his family for a long time because his father was a doctor and my friend was a doctor. He said, already studied that, gave it to me. What is a good thing with this skull, it works just like a Lego. It can take it apart, something like this. The reason why we can take it apart, because the person who had this skull probably was a lady, probably was about 18 years old, and in her stage, these elements of the skull was not grown together yet, just a little bit. So when they prepared for this demonstration, for the study, this soft part was removable, so I can take it apart. So this is the element what I want to point out here, what is responsible for the hearing. And if you are interested, you can come and take a look closer in a break, and you can see how small those elements are. What can sense the sound, what can sense the movement. It is something very interesting and fascinating. Some Hungarian guy, this guy here, Békési, invented how it works. That's why he got a Nobel Prize. We are very proud, very glad to learn how it works now. He invented the operation of or discovered operation of this so-called cochlea, the hearing sensor in our head. What is very important to know, it is very common that most of our sensory cells has small hair cells in it, and these hair cells can do the transformation to send the signal, for example, the frequency of the sound, to this pulse modulated signal to the brain. But these are very vulnerable. So if you are unfortunate to go in a concert and stand in front of a very strong speaker, it can damage your ear permanently. There's no way to recover, because our ear behaves like a frequency analyzer. It analyzes the different frequencies, and if one specific frequency is extremely strong, meaning that moving that hair cells are extremely strong, those hair cells can die. And if this hair cell dies, there's no way to recover. Or we cannot live that long enough to recover. Maybe 100 years it will grow back, but we don't live that long enough. That's why if you have a fortunate situation, that's why some of these speakers has a sound limit on it. So you can put a headphone or earphones in your ears, but if the device is well designed, there is some sound level limit in it. Protect your ear. Better to keep in mind, we can destroy our ear very easily, and this is a reason why very big percentage of the population has a hearing loss, because we cannot sense it, we cannot see it. It turns out when we are having audiogram, somebody is measuring the sensitivity of the area, so okay, there is a hole in it, that area is done and dead, something like that. And I don't go into the details, it's fascinating, but if you're interested, you can do it by yourself. But it's important to tell, this is how the graph shows the different sound levels. The minimum, but the most sensitive part, it is in a sound, in a speech range. It makes sense because it brings us the most important information. The speech is somewhere between 1000 Hertz and 3000 Hertz, in this range somewhere here. This is where all of the different sound levels are the most sensitive. So it is very important. And then if somebody has a hearing loss, meaning that this curve will go down, meaning that nobody will be able to sense the signal around it. What is a very important thing to know, if the hair cells are dead for some reason, there is a way to fix it. Not the hair cells itself, using some kind of prosthesis. Put a cochlear implant into the ear, bringing electrodes into this cochlea, and give a stimulus for the different parts of the cochlea, and it is a very standard procedure these days for those people who somehow has a hearing loss responsible from the cochlea. Another thing what I like to mention just very briefly, what is very fascinating for me when I learned, there is another interesting organ, sensing organ in our ear, inner ear, besides of the cochlea. it is extremely important. It is called the balance and the acceleration sensor. As I show you in this photo, even big range of creatures, animals, has the same structure: fish, frog, bird, mammals. What is interesting, we have 3 perpendicular sensors built in our ear, in this little bone. One is 30 degree up, like this here. Another is 90 degree like this. Another is 90 degree like that. Because of that, if we move our head in any direction, it can sense the movement. Not just acceleration, it can move the physical position of the head also. And the way how it works, I have this demonstration here. There are some hair cells in it, and this tube is inside of the bone. So when we move our head, the tube will move, but the water inside will remain as an inertia inside, and it will bend the hair cells in it. As you see this little blue dot, it remains in the same position because there is a water inside, and it has inertia. It can move freely, and it can bend these hair cells. This is a way how we sense acceleration. Interesting to know. This sensor, this organ, is the very first one what is developed in a little baby when he or she is growing. When the person is about a month old or a little older than a month old, it is already ready. Why it is so important? Because it gives a signal for the other sensors. For example, if we are standing like this, we need to behave differently if we are standing like that. First, the visual situation is different, and then the body balance is different. The tension, the blood pressure should be different if we are hanging upside down. So this is the key element for this movement sensor. And it's a big problem if somebody has a problem with it. No easy to fix, and the person cannot move at all. And this is the reason to have a motion sickness if this organ is somehow not working properly. Maybe it will be in a test. I like to point out here. We have 2 different sensors. These blue ones responsible for the static position. The green ones responsible for the acceleration. This acceleration, like this here. Interesting to know, in a human ear, there are some hair cells in it, and some kind of calcium crystals on top of the hair. So when we are moving our head, this calcium is heavier than environment. It will bend these hair cells, and we can sense this. And this is the way how we can sense the head position. Of course, we have muscle tension sensors also in our neck or in our other part of the body, but this is the primary sensor for head position. The green one, this one, responsible for acceleration, and these are perpendicular. It was interesting to learn that this one here is about 30 degree upwards. Maybe I marked here. Yes, 30 like this. It stays like that. The reason, probably, because we inherited from our ancestors, and originally it was something like that. But when we stood up, it was no problem because we used the software to reorient it. We didn't have to move the hardware. The hardware will be just 90 degree perpendicular anyway. But he relabeled it, and it remained like that. This is the reason why we have it. So this is the skull, what I'm showing for you. And if you are interested, you can come and take a closer look here in this second. We reached the point for the break. I'd like you to have a 5 minutes break, and after that, I'd like to show you a short video, and then I'd like to talk about the embedded systems, what is also a very important thing to know. Thank you. 5 minutes break.